Hey everyone, thanks for being here. Uh, there's a Miko going on. We have a couple of, I think a total of four in person. Justin's our presenter is here as well. So we're going to talk about KiCAD and how to develop or design your own PCBs. I'll let Justin uh, take the floor and tell us what to do.
Wait, before you start, where are you guys actually physically located?
Oh, hey Greg. We are up ESB 10 Devon, 10th floor, uh, towards the corner,
Okay,
where you have the graduate offices and stuff.
gotcha. Thanks.
All right. Justin, take it away.
All right. Um, so first of all, just a little background. We'll be looking at KiCAD. I'll link will the chat be linked into the recording as well? Will they be able to access that? Or
The chat.
yeah, if I like put the link.
Sure, I can do that.
So the download link for KiCAD I put in there. Depending on your operating system, obviously it'll be a little different. I'm on Mac currently, so results may vary. But as soon as you download KiCAD and start off your PCB designing journey, we look at, whoops, let me share my screen real quick. Instead of that,
I think it's an app.
share.
There's no way to mute it.
Can you allow me to share?
Oh, sorry.
Okay. Okay. You guys will get to see my entire screen, which is fun. Okay. There you go.
It's emails.
Look at my emails, guys. Okay. So we're here at this great meadow. You have this icon, KiCAD. We open up KiCAD, we get to this screen. Hasith, can you confirm for
I'm on Linux. I
Uh-huh.
see something similar,
see something similar?
saying like to automatically check topics. I don't know. I don't
Uh-huh.
need to run the tech manager, but I'm going to say, okay, I'm there as well.
Okay. So the first thing you're going to notice is there's a bunch of buttons. You can enter into different kind of sections of this editor through these tabs on the right here. We're not going to do that. We're going to do something that's more kind of encapsulating and makes it easier. We're just going to start out with a new project. We can name it whatever we want, but we're going to be designing a 555 timer today. Basically what that's going to do is we're first going to regulate down a voltage, an input voltage, say from battery. So we'll get a stable input voltage. We'll send that through our 555 timer, and then that will output a signal, a oscillating square wave. We'll be able to determine the pulse width based off of the resistors that we put into our circuit. And we'll also be able to determine a frequency with our resistors and capacitor as well. So let's get started. Ideally, you're going to be kind of designing a circuit beforehand, maybe by drawing it, putting it together on a just kind of, slotted board, a cracker board, beforehand, so that you know what kind of, resistors, and theoretically it might work, but once you put it into practice, it might work a little differently than you expect. So it's always good to put together a prototype before doing something like this, which is a bit more permanent. As you're, putting in the traces and all the components soldered on, it's a lot harder to change stuff on a PCB than it is on an actual, prototyping cracker board. So starting off our project, we'll give it a name. We could just do 555, little prototype. So we'll have this. I'll put it in my 555 circuit folder. So we'll save it into here. And once you do that, you now have two icons. One is a file dedicated to the actual PCB. So that's your traces, all of the different layers of your PCB and the soldering, the different footprints and components. And then the other one is the actual schematic. So these red little bits in this black line. So we're first going to open up our schematic. So .sch. So now we're here.
Just a quick
Yes.
question, just to confirm. So the schematic part is, that's where you deal with symbols.
Yes.
Like draw a resistor as a resistor symbol and a capacitor or whatever is going to be in symbols. But then the second one you were talking about, the green icon, is essentially where you deal with footprints.
Yes.
What is actually going to be on the board itself.
Right.
So the first step is to do the schematic first.
Yeah. It's
Okay.
basically converting from your hand-drawn kind of, system that you want to design, putting it into, you're basically deciding, all right, this 555 timer, what does it connect to? It's your first step into relating what you drew into the computer. And then from there, the computer will know what ports need to connect with one another. And it's a lot easier in building your traces with that. So first off, we're going to include the all-important 555 timer. Now, we want to do these modulations. Different 555 timers have different input and output voltage maximums. So I went ahead and chose one that's pretty good to my liking. How do I get rid of the hide floating? Okay, hide that. So the 555 timer that we have selected is this one right here, the SA555. So when you're kind of selecting these different items, you need to keep in mind what your outcome is. So this one has a maximum frequency output of around 100 kilohertz. So we won't be able to achieve frequencies above that. And the supply voltage that we can give it is between 4.5 and 16 volts. So when we're using our regulator, our voltage regulator, to control our 555 timer, we need to make sure that the output voltage is within that range. So
just to clarify, at this point, if you're building a PCB, all of these details would be figured out from a previous step. As in, you have done prototyping, you know exactly what you want. For this tutorial's purposes, you're telling us what your requirements are, and these are the things that you have chosen.
Right.
Okay, cool.
So we'll start out with this. Looking into the data sheet is a good first step into kind of designing your circuits. So if we open up this, we see there's a whole bunch of internal parts to our 555 timer, but what we're mostly interested is in kind of two things. The recommended operating conditions, which tells you what your supply voltage range should be and kind of the voltage ranges you can expect and current maximums. But we're also interested in seeing the applications of the 555 timer. So a lot of the time, these documentation sheets will have example schematics that really give you a good idea of how this should be set up. So we're going to be using the astable operation mode and basically stealing what they put in here and putting it onto our board. So this will be the first step in our kind of design. So we need the SA555. That will be our system. So going back to KiCAD, clicking the symbol
Justin.
button on the right.
One quick question.
Yeah.
Could you introduce what parts we are looking at, like in the interface itself? I see a blank sheet that I'm assuming is, sorry, when I say a blank sheet, the white sheet, that's kind of like your area. And like,
Oh.
what are the like, different
Yeah.
places to look at?
So basically, if we see our screen now, there's kind of two main sides pretty much. Right here, you have all of your, there's your symbol editor, your symbol library. This is your footprint editor. These aren't as important. One of the most important ones is your assigned footprints, which we'll come to later. Basically, for each symbol that you put down, you may have different footprints that are associated with it. So for one symbol, you have multiple footprints, so we need to decide which footprints we want to include, which is basically telling us the dimensions of the soldering pads when eventually this PCB gets built. On the right over here, we have our symbols. We have our kind of power and grounds that we can have here, lines to connect different ports of our components, and some closures just so that the system knows that one pin is to be left floating or stuff like that. So that's what this X does. The rest isn't used too much. Some for more kind of housekeeping stuff, but we'll talk about that if it arises. So the first thing we want to do is we've clicked on this triangle with a plus and minus, the kind of op amp. We come up with the symbol editor, and we need to find if the 555 timer is already available in our KiCAD library. So what we'll do is we'll check the product number, the part number. So we're looking at the SA555 is what we're looking at here. So SA555D, SA555, and it's there. So we have the SA555. Now, if we go back there real quick, you can see that this is the kind of assigned footprint. So a lot of the symbols, when they refer to specific components, will already have assigned a footprint. There'll only be one footprint for it. So this is the footprint that will be on the actual PCB. Those are its kind of solderable pads on it, and a brief description of kind of the package, which is the actual enclosure of the component and all of its, just some basic description of it. So we've added this on, and we see there's 8 pins. So the document sheet is going to tell you what all these 8 pins mean, but just real quick, we have VCC. This is the supply voltage. Q is going to be our output voltage. DIS is the discharge pin. THR is our threshold. R is our reset. TR is our trigger. And CV, I forget, but it's left floating and it's connected to ground, so it doesn't really matter. So basically what we're going to do is we're going to go through each pin and figure out where it needs to go. And that is told to us by this document sheet. So from here, we see that we need 1, 2. I don't know why this load resistor is there. I looked at other document sheets which didn't have it, so I'm going to omit it out of our design. But we have 2 resistors and 1. Note A says to include a decoupling capacitor attached to our control. Oh, right, CV, that's the control. But to attach to control and lead that to ground. And then we also have a third capacitor attached to our voltage input. So we'll put down 2 resistors and 3 capacitors. So again, going to our symbol component library up here, which is on the top right. We type in C. So that's going to be for capacitor. We bring that in. Now we have our capacitor. If you press R, that rotates your component around and makes it nice to orient. So we need 1. If we press escape, that cancels us out of our component kind of adding. We click on the component, Control C, Control V allows us to copy and paste, and we can get 2 more capacitors. So we have those. Now if we add in our resistors, just R, and you'll notice that we need 2 resistors, and these have no footprint specified. Resistors and capacitors, they're very generic, so they come in different sizes and different footprints. So you're not going to have one specific one for it, and we'll need to use the footprint assigner tool when we eventually give these a size. So back out of this. So we have our capacitors, we have our resistors. Now we just need to add them on. So we look at our schematic, we see that we have a threshold and trigger coming together. So what's nice about KiCAD, you have these little circles at the end. If you hover over it, you have this plus line. So that's just adding a connection between 2 of these circles. So we want to connect threshold and trigger. So threshold is here. And if we click while it's, see how it's like, you know, you get 2 lines out of it. If you click again, that kind of locks in where you were just at and allows you to continue on. So clicking there, and then we can bring it in. So we've connected threshold and trigger. We then need to connect that to a capacitor, which can be this one. So if we connect that line to a capacitor, and then we need to connect it to ground. So using our pin here, our kind of power and ground symbols, and go over here, type in GND, which is for ground. Yeah.
So essentially, to add stuff, you just click on the circle and then click on the other thing.
To add stuff, click on this. Yes, you're just going to click on there. You can also click on the symbol below power symbol, and that will be your add wire icon.
Okay. Okay, the W washer.
And
then the ground you added here.
right. So G and D, so that's basically defining any pin that you connect to this G and D will basically as if they're all connected together. It's all in the same kind of ground plane. So we've connected up our capacitor. We see that there's also a resistor that's above that. So if we have a resistor here, we can connect that to our kind of detach pin or our detect pin. So that's this here. So clicking and rotating it around, we now have that resistor. Now we have another resistor that leads to power. So adding another power symbol, we can say, and like we had said before, we want 5 volts about. That's within the range of our 555 timer. So if we type in 5 volts, we can say this will be a 5-volt kind of power plane. And adding that onto there. So we have 5 volts coming into that resistor. We also have 5 volts connects directly to our reset, which is right here. So we can kind of either, you can take it out to another plus 5 volts pole, or you can kind of add it up there, but be careful not to take your line across open pins because that'll automatically attach them. So if we go out 1 and then kind of go up, that will avoid using that, and we can kind of attach there. So that's connected to 5 volts now. In order to move our components, we're pressing M once you clicked on them, and you can move them there. So we have our reset pin connected, and then there's a 0.01 microfarad capacitor connected to ground from our power voltage. So if we take this here, take another, ground, place it there, connect. So that's our capacitor here. And then we have ground connected to ground. So we can take this, ground, and then we still have another capacitor. This capacitor goes to our control pin, which is our CV pin. Whoops. That connects there, and then that itself connects to ground. And we have one more resistor. So we have a resistor in between here, going up to there. So that is between our discharge pin and our 5 volts. So if we press delete, we can get rid of that. Add our resistor there. Between the trigger and discharge. Trigger and discharge. Oops, I have seemed to have messed up a little bit. Okay. So we have a connection between trigger and discharge here. So this connects to trigger and discharge, and between them is that resistor. Okay, and then from discharge, we need a connection to our power. So this needs to be here and there. Okay. That seems right. And then VCC, that's our supply voltage. So that will just go to 5 volts, as is shown there. Okay. So that's everything connected. That's great. But now we need to be able to supply our board with 5 volts. So we need to look at voltage regulators. So these voltage regulators are going to be.
Couple of questions.
Yes.
So these capacitors,
Yes.
when you were selecting capacitors, does it matter if it's electrolytic or ceramic? Because they have different footprints. Or
Right.
is this a selection that you do after we are done with this?
You do that after.
Okay,
If
I
we.
see. So the reason I was asking is I'm used to doing this stuff in Eagle, and in
Mhm.
Eagle, the way it works is you pick your footprint. There is no option of changing the
Mhm.
footprint afterwards. You pick everything when you start here.
Right. So this is not the case.
Okay, I see.
So we've gone through of how to add in
Right.
components, how to kind of select them, making sure all voltages are correct, how to move them around, and how to navigate around our device.
Gotcha.
So I'm going to open up a project that I was working on, which includes the voltage regulator and an LED. So if I just go back to save this, kind of exit out of this, and then go to our list. So going back here, opening up my other project. So this is the same circuit, right? Slightly different. This is for 3.3 volts. But we see over here, this is our voltage regulator. Basically, it's following the exact same thing. You kind of go to DigiKey, you find, okay, what voltage regulator puts out a 3.3 or 5 volt output. You follow the schematic that they give you on the document sheet. And as long as all of the parameters match what you need, you plug it into here, wire it all up, making sure that kind of your external connections, right? Because if we're running this off of a battery or a series of batteries, we need to make sure that we're including that and able to interface with those batteries. So we have 2 pin connectors here. And if you type in CON, which is the abbreviation for connectors, and then maybe put in 2, you can kind of 2-pin connector there. So a little bit of, knowing what the names are in the actual library, but once you start to add in connectors and various things, you can find them fairly easily. But so we have this regulator, it's converting whatever the voltage of battery is down to 3.3 volts, allowing us 800 milliamps to power whatever device we want. So that 3.3 volts connects over here. That goes through the circuits that we had put in earlier, supplying our 555 timer and outputting a pulse width modulated signal. Just like in the example plot shown to the right. So this will have some sort of amount of time that's high, amount of time that's low, and then oscillate at some frequency that we determined based off the resistances we input. So putting those in, we now want to kind of drive something with it. So for example, we have this LED. So the output of our device is going to be output at 3.3 volts. And if you were to look at an LED, you'd find that there's a certain amount of voltage across it that it's going to take, and there's a specific current that it wants to operate at. So since we have a kind of series circuit here, we can do a little math. So if we go to below here, there's this text, add text. We can type in kind of our bookkeeping for our circuit. So this basically lets us be like, here's why these resistors are a certain value. Here's the equation that I used to determine this. And that, so if anybody else looks at your circuit diagram, they can be like, oh, that's reasonable. So just adding this in. So we're going to have a 3.3 volt kind of overall. And then we'll say, I'm not sure, I haven't chosen a specific LED, but maybe it's like 1.3 volts across it. And maybe it's, I don't know, 0.2 amps, very large. So the LED requires 0.2 amps across it. LED requires 1.3 volts across it and a current of 0.2. Pressing OK. We can define that there. Now, from our kind of EE background, we know that V is equal to IR, right? So we know the current for a series circuit is the same for across each element. So we know the current of both of these components, and that's going to be 0.2. So we know that I equals 0.2. We also know the voltage across the whole thing is 3.3, right? And the voltage across our resistor needs to be, 3.3 minus whatever the voltage across our LED is. So that's going to be about 2 volts. So the voltage across our resistor is equal to 2 volts. And that's going to get us the amount of resistance that we need to drop the voltage to get it into what our LED wants. So putting these into our equation, we get 2 divided by 0.2, and that's going to get us 40, 100 ohms, all the same thing. So R equals 40, but for these purposes, it's pretty all right to add a 100 ohm. So based off that.
So one question here,
Mhm.
as far as the program is concerned, this value has nothing to do with this specific process, right?
This you'll need to,
If you want labels nicely on the PCB,
right.
sure, I understand that you
Yeah,
have,
yeah.
oh, this is a 100 ohm resistor. But if you wanted to,
It makes no difference to the software.
Right.
The only thing it cares about is what connections are made and what's the footprint.
right.
Uh,
So essentially, I could be like, oh, I don't want to document the value here, but if you wanted to, this is how
Right.
you would do it.
you could say R3 is
500.
500 ohms and have that on a separate sheet,
Right.
and
Sure.
that's fine. I typically take this. See how there's 2 kind of labels here.
Right.
I typically take the bottom label and replace that with what it actually is. So for example,
Oh, the
40
value? Is that
ohms.
what you're saying?
Yeah,
Okay. So you're using the bottom label R as the value?
right. Because
Okay.
the bottom label is just specifying what the component is.
I see.
And so for resistors, it's just going to be R.
Okay.
And so I just replace it with
Sure.
that.
One other question,
Mhm.
just in the Eagle world, what you can do is at the end of the day, you can generate a bill of materials. So for this specific circuit, will
Yes.
that go into somewhere? Like if you put 100 ohms there, will that translate? Can I generate a BOM and like look at a sheet and be like, oh, let me order all of these components. Can that be done?
It should.
Okay.
I believe it prints off the component
And the
name.
value.
Yes.
Oh, okay. Awesome.
It'll be like R3, which is
Right.
40 ohms because I replaced it.
Sure.
Or it'll say U2 is SA555D.
Sure. Works.
So I replace it with that, so it's easier for me to know. And then when you generate a bill of materials, you can
Okay. Works.
determine that.
Just curious.
Okay. So we have this resistance determined. Let's start adding some footprints. So these are what's actually going to go on your PCB. All we have to do, click this little button up here. It's got that little symbol thing, and then those 6 pad device right there. So assign footprints. It is the one next to the sine wave looking one, the simulator button. Yes, assign footprints. So now we have this thing. A bunch of yellow stuff, and you also have our voltage regulator and our 555 timer, which already have their assigned footprints given to them since there's only one footprint for it. Capacitors, the diode, our connector, and our resistor, there's multiple kind of products for it. So there's multiple footprints for it. So we'll first kind of double click on the first symbol there, which should be capacitor 1. We have written here that that is our 0.15 microfarad capacitor because we've been changing its label to make it easier on ourselves. These I didn't do, but they should be 0.1 microfarads. If we click on these buttons up here, this is basically how you filter through this right section, these filtered footprints. Basically what it's doing is taking, for example, if it's a 6-pin connector, this will filter it by how many pads it has. So you can have a footprint that doesn't match your component if you don't click this button, which might not be useful. You can also filter by actual libraries over here, which I tend to not do. Usually clicking the 2 buttons on the left and in the middle gets you the most accurate pads that you can use. We've now filtered it by clicking these 2 buttons. We can now kind of look at all this mess over here. So our capacitors have a couple things about them. If we expand this and this. So basically, these numbers here are different sizes. I believe one's kind of in mils or in like kind of milli-inches, thousandths of inches, and the other is in metric. So 0201 is always going to correspond to 0603, just difference in units. But as you go down this list, you can see the numbers get increasingly larger. Yes, Hassan?
So in my view,
Yes.
I have devices saying SMD and through hole. So is this a choice that I have to do at this level? Do I want an SMD component or a through hole component? I'm assuming that needs to be done here. Why is it not showing up on UORs? I don't see
Where does
SMD.
it say through hole? I have THT.
Yeah, TH something is through hole, I'm assuming, right?
Right.
So at this point, if I want through hole components, I need to pick a through hole thing.
Yes.
Okay.
Yes. So if you want it through hole, this is we're deciding how big of a capacitor and what type of capacitor at this stage. So we're deciding on the size. So obviously, the larger the size, the easier it would be to hand do the work. So
Say we should go with through hole because if you're making it's easier to solder and stuff.
sure, yeah.
Or I don't know for this matter, but
Yeah, we'll update it once we get there, because I've only done surface mounted, so I don't know the other
Also, you are doing 0805, I'm assuming that's the size usually typically.
yeah, we can. I've done 1005 was just because it's a little easier. But basically for 1005, there's kind of 2 options, a hand solder option. This is just basically the pads are a little bigger, is the difference. So if we select our 1005, and then for each capacitor, make it easy on ourselves. And now we get to the LEDs, very similar. You're just selecting the pad size. So in here, we don't have 1005, but we do have 0805. So we'll select that. And now the connectors. So I typically go down to pin header and pin socket. Now, the most kind of generic sizing for this is about 0.1 inches between each pin hole, and that's going to correspond to, I believe, 2.54. Yeah. So that'll be 2.54. Now you have different options on the right here. So you have horizontal connections, which just means that they're going to be in the same direction as the PCB, so they'll be flat, and then vertical, which will be up. And then you also have surface mounted instead of through hole pin sockets. So a pin socket is kind of referring to if it's going to be, something is going to be placed inside of it. So if you had a male connector, that would be inserted into the pin socket. Pin header is when you have a exposed conductor that's pointing out. So we'll choose our pin header, and that'll be 2.54, and we'll do it in the vertical alignment, which is just pointing out. So that'll be our connection. The resistors, very similar. 1005, hand solder. And then we've selected all of our footprints. So once we've done that, we can press OK. That should be all fine. In older versions of KiCAD, you would have to click this button here. What this does is it annotates every component. You can see that you have things like C3, R1, R3. In older versions, this would just be C question mark and R question mark until you clicked here. And then it would automatically annotate from the top left down to the bottom right, assigning it a number as it goes. But in this version, it's automatically doing that, so we don't have to do it. But if you wanted to refresh the numbers so it's easier to kind of control in your mind, if you click that, it allows you to sort out the numbers automatically. So close out of that. Now we're going to go to the PCB. So clicking on that green button in the top right, so right here next to the bill of materials, to the left of our script writing thing, we'll switch over to here. We now have a dark screen in contrast to our bright schematic screen. And the cool thing about what we did at the beginning was when we clicked create a new project, it allows us to pull all of what we did on our schematic into the PCB. And if we make changes to the schematic, all we have to do is press this button, update PCB, and it will make changes to our actual PCB layout, adding new components, changing the connections, and all of that. So it's very useful to start with the project like we did in order to get this button to appear and allow us to do this. So this is telling us, hey, everything's good. You've assigned all your footprints. Nothing was wrong. We just click update PCB, close out of this. And now we have all of the components that we had put in previously now appear here. So these are the footprints that we had assigned to each one of our components. And you can see that there's these kind of little blue lines. So those are the connections we had made during our schematic phase. So that will help you with kind of your preliminary laying out of your board and just in general, like make life easier. So we'll go
Hey,
through.
Justin.
Yes.
Quick question.
Yeah.
So I have the schematic done,
Okay.
values were fixed. I selected all the pads.
Yes.
So I flipped it to the black screen,
Yes.
but mine is empty. What did I do wrong?
Did you, so we clicked the update PCB from schematic button,
Update, okay, got it. I see.
and that should bring up a kind of screen that
Mhm.
tells you,
Right,
Right.
okay, update PCB.
yes,
I don't see any warnings, no errors.
right.
I see. Okay, yes, thank you.
So
Sorry
now
about
you
that.
have all your components.
Right. In like a small bunch.
Right. In a small bunch. So now we're kind of just going to move our stuff around by clicking kind of in the center. So you can see that these are quite small,
They are, yes.
but if they're too small, you can always go back to your schematic, make the footprint size bigger, like we were talking about, and it'll be easier to solder. But
One other question.
yes,
I'm seeing a bunch of grids. what scale are they? Or at
These
least this is
grids.
me,
So,
default window, I see a bunch of grids. In
okay,
in Eagle, you can typically change the scale of it. Oh, this is in mils, this is in millimeters, all of that jazz.
right.
Is it important
So
to get
in
a
the
sense of
top,
scale?
there's a 0.5 millimeter thing right here. Do you see that in yours?
Sorry, could you, like, shake him out? I can't figure, oh, okay, I see. What are we thinking?
Right. So to the right of kind of this red and blue thing, there's 0.5. This
I see.
determines your kind of grid
Base
scale.
Okay,
Right. So if I click 2.5, we now see how our cross kind of moves across in more spaced out discrete steps.
right.
So that's going to determine where our component can lie.
So what's your typical recommendation?
So I usually go with 1 millimeter.
You're doing it in millimeters. Okay.
Yes, this is in millimeters. You can do it in inches as well, or mils, thousandths of inches.
I think like in PCB world, the reason I asked was PCBs usually the pin spacing is in mils, as in 0.1 inches is the measurement. That's why I was curious, right?
Yeah, and you can do that. So 0.1 inches would be 2.54 millimeters. So let's just do that.
Okay.
So we have that here. So we click on the entirety, which is kind of off, because if you click on a pad specifically, you're not going to be able to move the whole thing. So we click on everything, press M, and that's going to allow us to move our device around. So we see these blue lines here. Move this around, see where it needs to go. Those are both in the ground plane. So pressing R, we can kind of rotate them around. Yes.
I'm sorry,
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 sorry.
one other question before getting into all of this. So in a PCB, you may have multiple layers. Are we working on one specific layer right now, or is it in general
So we
unassigned?
have not defined the
Anything.
layers yet.
Okay, so this is just, we are placing stuff.
This is
somewhere.
us placing stuff, getting it in the orientation we think is
Okay.
good.
To change.
Yeah.
You can change the grid, but can you change the actual spacing as you move? Because I think the two are separate, aren't they? You have a grid, and then you can also choose how fine of a movement your piece is going.
So if we were to go to, say, 0.127, the grid so we have much more fine movement scaling. So the grid and the movement, I believe, are connected together in that if I change now the grid to 100, and we can see that the dots are now much further apart, but moving it now, we can move it back to where it originally was. But so I believe the grid, and you might be able to change that in the settings. There might be a button here which locks something like that. I haven't looked into that too much, but this is typically how I change it so that I get even spacing between my different components. But if we kind of move everything around, we have our grounds. These need to be attached to here. This goes to that there. Now, these should be pretty close to our device, so we might want to go a little finer in order to get kind of there. And you see that turned red. So it does tell you if you've overlapped your components. You see this here. So this connects 3.3 volts in ground. We can kind of put that anywhere. Kind of get that close to our voltage regulator, which we'll put up here. Now this is going to connect over to here.
I guess this part is kind of like based on skill and previous
Yeah.
experience that you have to figure out where stuff would make sense to go, right?
Right. And, this is where you can put a lot of time if you want.
Yeah.
We're just kind of getting everything spaced out so that it's about where it should be. This is again 3.3 volts in ground. So that can kind of also go, close to this because they're
No automatic PCB layout, no special red button.
I haven't found it. It might be there. I'm not too sure. There could be.
Question for even eco, I'm new to KiCAD, I'm just learning, and even for eco, you can't place the components automatically, you have to make the layout, and it has auto routing and stuff, but not in place.
Yeah, and I don't even know if this has auto routing. So we have, this is going to need to go to 7 and this is 4.
It's open source, so.
No, it's definitely, and I was running on a much older version of KiCAD.
Oh, okay.
And a lot of this stuff wasn't in that either.
Oh, really?
Like yeah. It's gone a ways. And then just putting these in, we see that this is between those two. So put that there. This is just a ground, so it's okay to be there. This resistor needs to connect here. This is our 40 ohm resistor, which goes to our LED, which we can kind of place. It was pretty good. Okay, something like that seems pretty good. Now we have the general kind of layout and size of our device. So that should be 3.2 volts. This should be connecting to there, and we can kind of, that'll be good. Okay. So one of the things we need to do is now define our boundaries. So it needs to know where to cut, basically. When it's printing out the PCB, we're going to have this big green sheet of material, and it needs to know where we're going to be cutting. So that's defined by our edge cuts. So this gray one here. So these layers are all the layers that you can kind of have throughout your PCB. We're going to be focusing on a 2-layer board for today. But edge cuts is where it's going to cut the edges to. So we click this box here. You could do a circle, you could do some sort of polygon, anything you want. I like boxes. And then we just do that. And now if we let me hide this loading command. If we go to view, 3D viewer, that gives us a nice preview of kind of what our board would look like so far. These things are extremely small, so we might have messed up our assigning our footprints, but that's okay. So that gives you a preview basically of what's going on. You can flip it around just by clicking and looking at different layers, and then moving around with these arrows. But if we go back to our device, we now want to give it some planes, some copper layers. So to do that, we can click on FCU. So that is kind of our front copper plane or our top copper plane. We do the same thing, basically just clicking a square, going from top, whoops. Sorry, not the square. We want a filled zone right here, which is under our vias, which we'll talk about a little bit. But clicking on filled zones that's basically going to tell them that all of this through here is going to be filled with copper, and we're assigning a specific kind of power or ground for that. So we had two kind of power plane symbols that we assigned earlier. That was 3.3 volts and ground. So for our top layer, we'll just put in 3.3 volts and keep that. And then click, whoops, 3.3 volts. Okay. And now you have this line. It's basically wanting you to draw a polygon. So I'm going to go around in a square instead. Click, click. And then once you get up here, you're going to double click. So click, click. And, or just click once. That's interesting. And now we have laid out basically our fill zone. So anything within this zone is going to be a copper at 3.3 volts, and it will connect to any pin that is 3.3 volts assigned. So now if we press B, that will automatically fill in all of the copper into our little area, neglecting all of the stuff outside of our cut zone, and give you these nice little thermal reliefs. You can, of course, change that, which is down here, pad connections. If you want solid fill, for example, that, and pressing B again, you now have just a solid connection to it. I don't think these are going to get too hot, so I don't think it matters too much. And it's not too much current passing through it, so having smaller connections. So either way, it's a good little thing. You'll notice that, yes.
All right.
Okay.
Just can you back up a second and recap what the last few processes were? Like,
Yes.
I have right now, I have a schematic. I have the parts placed somewhat okay, push. I had to go back and update certain like packages. I took a little bit of time, so if I have everything, the next two things is set up a box.
Right. So you're going to go to edge cuts. Edge cuts is the boundaries of your PCB.
Yes, I see it.
So
But that's fine.
this gray. You'll then use these kind of shape tools.
You usually use a rectangle, I'm assuming?
I use a rectangle, and then you can also use draw arc to get kind of, corners.
Oh, I see. Yeah. I
And you
just
can get
draw-
like,
do a rectangle, that's fine. Okay.
so you have your
That's the
rectangle.
good stuff. Is it draw line?
What?
So I have a rectangle.
Draw a rectangle. And then you click,
Oh, you click, I see.
click, and then, you click once and
Okay, gotcha. All right,
Yeah.
yes, pick it up, find it. I'm gonna get the size as well.
Interesting.
Sure. Okay, once I have that, I'm there. I have
So-
bounding block there. I'm sorry,
you have your edge cuts. And now you want to get a fill zone.
Okay.
So if you click your top layer, FCU, so if you click there and then go to fill zone, which is under the orange circle, add fill zone, and then
inside that small box again.
outside of the box, you're going to click, a window will pop up. You're going to decide if you,
I'm gonna go with ground, understood.
okay, so you select ground, click OK, and then some lines will come off it. And then you're gonna click on a corner and basically make a square.
This is like you, essentially, this is the enclosed region that you know fill.
Yes.
Okay.
And it will automatically say if it's outside the edge cut, I'm not gonna fill it. It doesn't
I
mean
see.
anything.
Okay.
So
That's why you selected the bigger box.
Right.
Now mine shows like, it's not showing me red.
So this is, so if you press B, B updates the fill zones
Okay.
and everything.
All right, thank you. I'm there.
Okay. Oh, no problem. So since we're making a two-plane board, we can add another layer. Yes, right. So we have bottom copper layer here. We can click our fill zone and do the exact same thing, but this will be our ground plane. Okay. Now we've put these components on the top of our board. So the solder pads on the footprint are going to go to the front plane, which is why this kind of separation between our copper plane and our pads is there, because we've told that this copper plane is meant for 3.3 volts and only 3.3 volts. So these are left unconnected to our plane. Now, the bottom copper plane is set to ground. So if we press B, we can see that's now like a purplish color. But this whole plane is filled with copper because there's no components on the bottom. So there's no need to, separate footprints from it. So we have a full ground plane on the bottom. If we press F, that didn't do it. Oh, what's that flipping? There it goes. If we press F, that's basically flipping whatever thing we have selected. So for example, we assigned this layer to be on the ground plane, or to be on the bottom layer. We press left or F, it's now flipped over to the other side to the top layer. So if we press F again, that goes back to the bottom layer. We can put it back. Similarly, if we were to
So
click.
if I want to flip a component, I
Yes.
select the component, flip it.
Right, so if we selected our voltage regulator, pressed F, it's now on the bottom. And we can see that if we go to view 3D viewer, I didn't update the planes, but we go to the other side.
How to get the
The top left, or at least on mine, there's a button called view,
okay,
and
you right in mind.
and it should be 3D viewer.
Yeah. Okay, got it.
So we can see that our component is now on the other side, after we pressed F. So I'm gonna bring that back by pressing F again. And now everything's a little hard to see because of the blue and purple. But if you click this kind of eye icon, it hides those layers. So the bottom copper layer is now hidden, and it makes it a little easier to see.
Going to the bottom, right?
Yes, so I hid the bottom layer. This is now seeing the bottom layer. So now we need to connect everything up. This button right here, this is route tracks, which is basically your traces.
One question,
Yes,
you say connecting stuff. Essentially, this is the PCB that you would produce, right?
yes. If you went to view 3D viewer, this is what your PCB would look like.
My question was, packing the part with, you have to specify for, like, for example, let's say you have a high current carrying wire
Yes.
and you need, I don't know, however much thick copper.
Mhm.
Is that already specified here, or do we have to do it next?
The thickness of the copper layer itself,
Not the thickness, but
the trace
Yeah.
width.
trace width, yes, that's what I.
So we can go to, so now that we have all of our layers and stuff defined, if we go to route tracks, route traces, we can start connecting stuff. So in order to change widths, like Hasith was talking about, we go to the top left, and we can edit.
Or you can have next
The-
classes.
Right. So if we edit the predefined sizes, we can say add a new width. Maybe we want 5 millimeters, something like that. click OK. Track. And then if we go back to our little selection, we see that 5 millimeters is selected. Click here. It's very big.
Yeah,
And
so
then
I did that, but
Mhm.
how did you connect it? Oh, you have
it was
to
so
go back to
big,
the
I don't think it allowed me to actually do it. How do I do what?
No, I figured it out, sorry.
Okay. So we can, of course, go back, edit that size. What's a reasonable size? Like
This is what I usually know, I don't know what.
12 mils.
You can just type in
I
mils,
think,
it will detect.
oh, it does it?
Usually works on.
12 mils? You think that'll work? Yep, nice. Okay, so if we click our trace and then it automatically kind of jumps to our pads. It doesn't really matter the grid sizing for that. But we click here and then it kind of locks to our grid at that point. But we can bring it down, connect it. You now see that blue line has gone away.
So essentially those are unrouted traces.
Right.
blue lines.
So we can just kind of connect all these up, making nice little connections. We have ground here. Now, the cool thing is, since we've defined a ground plane, we don't really have to combine all our grounds together through the top kind of copper layer. What we can do is take out a trace and then press V. V for via. That adds a little button there. If we click again, that now we're in the bottom plane layer. We're creating a trace in that plane. We don't really want to make this trace because we're already where we want to be. We're in the ground plane. The via will connect to this ground plane because it's, wants to connect to ground. So if we press escape, it cancels whatever blue trace that it was drawing out and goes back to the via which we had already created.
Really practical question. I
Yeah.
guess. So if you were to send this off to PCB way or something like that,
Mhm.
when they create those vias, they fill them in so that they are going to the other side of the board and the connection's there.
Yes.
So
Now,
that,
if you do that in the innovation hub,
Mhm.
they have their boards that's available to you. I don't think that's
So-
available that way.
they have a small punch tool now. Yes, so what they will do is, you're right, so the innovation hub, that is potentially something that we want to do after this training. Once you have a PCB, everyone has designed their own. What they will do is you get a double side PCB, you etch whatever you have on both sides. It will drill the hole for you. What then you will do is you have a small, a rivet, if you will, put it in there, punch it. So that will give you copper on both sides and a internal small copper pipe. So,
With that being said, the vias are a standard size.
correct.
Okay.
So that you will have to, like, if we are actually manufacturing here, you'll have to get the specification from them. It's a standard size, they have a specific manufacturer, just get that and make the hole that size and that'll work out. I have tested it, I know robotics folks do that very often, they get the PCBs made there and they can do that. Like, I have tried it a couple times, it works.
I know that they can drill the vias
Right.
and push come to shove, I guess you just fill up some solder.
Like, I think pulling up to. My thing is, I usually, if I'm going that route, I would make it a single side PCB. That's what I have found to work, and you don't have to worry about wires or anything like that.
Right.
And for most projects, even this one, you can get away with single side, maybe put a couple of jumpers, like wires, but actually not using, just put a wire instead. That
You
can be done.
just put a pin to it,
Right.
solder on both sides.
That's kind of it.
And this is it. So we've gone through using our trace tool, basically clicking, pressing V to bring all our ground pins down to the ground plane, which is on the other side of our PCB, our second layer, and connecting the rest of our components together with our 12 mil trace width definition. And that's it. I press B, that updates our different layers. It automatically determines the kind of distance between our traces and the plane and fills everything in. So theoretically, if we connected everything right in our schematic, this should be a working board.
Can you see the 3D view again?
Yeah. So if we just hide that, go up to view, 3D viewer. We now have the vias shown there, our extremely small capacitors, and our two terminals, or our two connector holes 0.1 inches apart that will connect to a battery with a connector. And on the other side, you can see our via layers go all the way through and they connect to our ground plane. Same with our connector. This is just a really big via that connects to the ground plane, which is why we didn't need a trace up here since it's already connected through. It's a little difficult navigating the spin, but yeah. We can also add some little nice details. If you go to the silk screen, you can see that these different designators highlight. We can move them around so they're not overlapping anything. And we can even add in our own kind of text into this layer and images. I add images all the time. And we can just be like, Justin's 555 PCB. And then always good to maybe add a date, you know, version 1. That's a little big. Of course, we can change the size. Maybe we want it 0.5, 0.5, something like that. So, whoops.
I think we never talked about some of it, but like there are
That
certain
makes it a little.
good to do things like when you're routing, like, you know, high speed traces and stuff like that, like not make 90-degree bends.
Right.
Don't make it under other components, like if it is.
Right.
Especially if you're in radio stuff and you're doing RF things, those matter. This is like
Yes.
the bare minimum of things that you have to think about,
Right.
but there are other. things
There's tools like that on here. For instance, this button, I believe,
Sorry, you said-
creates. So
Oh,
this
it's
one,
fine with the path length matching?
yes,
Does it do path length matching automatically?
yes. So if I were to, you know, click on something and then you could do nice little, in order to adjust the length so that you can have some impedance matching, stuff like that. But for our purposes, this is
So,
good.
Maybe a couple of questions.
Yes.
Say. This is like. Low level speaking, this looks nice, you have stuff working,
Mm-hmm.
is there a way to do ERC or like? In Eagle, we call it, I think it's dimension checking or like, oh, hey, these two components are closer than. The recommended amount or something like that, like, oh, okay, I moved a component or I moved a trace because of some spacing issues. And like, oh, now these are like, oh, slightly overlapping or stuff.
Right.
Like when it comes to manufacturing.
So
Can you do this? I know that this can be done in Eagle, so I'm just curious.
there's a basically design rules checker tab right here between update PCB and switch to schematic.
Oh, I see.
So this is where you're going to click, and basically what it will do is, you know, if you ask it to basically do everything, it'll check if what you have in your PCB is the same as what you have in your schematic. It will make sure that all of your zones aren't overlapping and all the connections are properly made. For instance, if you're running traces and you end up kind of isolating a fill zone such that the copper plane is no longer connected to your 3.3 volts, it will tell you like, hey, this is no longer connected. And so it does do a good job checking that. So if we run through, there's a lot of errors. Actual. Interesting.
So that layout, did you like the way down, my layout has a lot of,
Mm.
like, my layout is right now. I have a lot of crisscrossing and stuff like that.
My assumption of what's going on is that the clearance of our pins, because our things are so small,
Okay.
I believe the clearance associated with it is now kind of impeding our other footprint, which might be what the errors are. We can go back to our schematic, click on switch to schematic, and
I
then
think, yeah,
simply
we can kind of
do
go that, but like,
this.
one of the other parts I was interested, say there's no errors. You want to export this, or you want to, you know, put a PDF out or whatever, like you want to send someone, like one of the things, say I'm doing a project, I want to make some documentation.
Yeah.
Save this or share this. Could you show a little bit about that? How to do that maybe?
Yeah.
And like, maybe after that, how do you export it to actually manufacture it? Like, I know Greg was talking earlier,
Mhm.
eBay or someone. How would you export gradle files or whatever, GRBL files to send it to a manufacturer?
Right.
If it is
So
too long, we might cover it later on as well, I don't know, but.
basically what it is at the end of the day is your, oh, there you go. You can have an add-on that basically converts your layout into a Gerber file. I haven't added it on to here.
Oh, don't worry about it. Yeah,
but-
we can figure out.
Yes, I believe there'd be an extension that you can then make into a Gerber file and then send off, and they'll have
I'm
it made.
assuming this being an open source project, documentation is well maintained for stuff like this. I mean, no,
There's-
because there are some projects that has really good documentation.
There's very good tutorials on YouTube and on and there's forums that talk about
Got it.
KiCAD. So it is pretty well documented. And of course, updating the footprints, you need to now update the traces, but
So that's what I had to do as well.
Yeah.
I changed the component, but now the trace is all, but
yeah.
okay.
So and something kind of useful if you find that you've changed everything about your design, bottom right here, there's a selection filter. You can kind of just select tracks,
Oh,
go
I
over
see, okay.
everything. And then if everything's messed up.
Oh, you just can
So,
get rid of all.
yes,
Yeah,
so you can, and if you only want to move, say, your actual components, you can select. For that.
You have to press B to get rid of the
Yeah,
trace cuts.
Right, pressing B again gets rid of that, and then get rid of vias, you can press that. So very nice. There's plenty of, I'm sure there's tons of tricks and little things in here that I'm not aware of. But yeah, this was,
It's a great song.
Yeah.
I was eager user for a number of years.
mhm,
A lot of the tools look very familiar.
Yeah.
But it's great to get a kind of a recap of, yes, this is what, maybe one other question, like.
Okay.
Say towards the project, what we are doing.
Mhm.
We wanted to share this file. Okay, I have a schematic, this is my goal. What do I need to send to someone, or if I'm putting it on Git or something? What files should I save? Or is it just a folder we create?
the Gerber file. So it's going to have all of the different layers.
What I mean is that is for manufacturing, right?
Yes.
What I'm saying is, I and you are collaborating, let's say, and I want to send my updated code into you. What should I, like, email you or whatever?
If we both were using KiCAD,
Yes,
you'd basically save the project
and you build the project.
and send that to me. Because then I'd be able to switch back and forth between schematic and
Right.
and the actual PCB,
And,
and that
uh,
contains all of the stuff
Okay,
along with it.
and one other question, are these
Uh-huh.
like text files? Like, can we keep it in Git? Because Eagle, I know for a fact, are text-based files. So anytime you edit, they're not binary files. They'll, add and append stuff. So is that still cool here or?
I don't know. I think. Yeah, I'm not too sure. I haven't added anything to get,
Oh, so, see.
not a
Eagle-
schematic.
Yeah, Eagle schematics are very compatible with Git. They're just text and XML.
Mhm.
It's not really. Okay. Yeah. All right.
All right,
So I see.
save. Nice. What's this?
Okay, so for anyone online.
Anyone online, are there any questions or things that you want to ask?
For questions after.
What?
Just an hour, hour 15.
Yeah.
I mean, I enjoyed it. I think I can make my own PCB now, so I'm
Yeah.
happy about it. That's the idea. But
Good.
thank you very much, Justin, for showing us how it's done.
Of course, of course.
Hopefully down the line, what I think we can do is if people wanted to get a board made for these things,
Mhm.
once you have a finalized schematic and you can get yourself trained to make this in the hub. But I don't think we'll have, it needs to be done personally, the
Mhm.
training you need to get from the hub, but it is free. You can sign up yourself. We gave you the tools to design stuff. So you can make that board and be like, hey, I want to make this PCB, get yourself trained there, and then you can test it actually. And if there is enough interest, we